This call is now being recorded.
Okay, so last meeting we stopped at section 2.2. So let us now proceed to section 2.3. We have moments and moment generating functions. This is actually the last section for chapter 2. And after this, we're going to proceed to chapter 3. And I'm going to discuss actually the last part of chapter 3. And the first part of chapter 3 will be for reading assignment. Okay, so let me proceed now. First definition, for each integer n, the nth moment of x or the nth moment of the distribution of x, denoted by mu sub n prime, is equal to the expectation of the nth power of x. So the nth moment of x is simply uh, means that it's the expectation of the nth power of x. And then the nth central moment of x uh, denoted by mu sub n will be equal to the expectation of the nth power of the difference x minus mu. So this mu here in the definition of the nth central moment of x, it refers to the first moment of our random variable x, which is actually equal to the mean of x. Another definition, we have the variance of a random variable is actually the second central moment of our random variable x. So by definition, it's equal to the expectation of the square, or the square of the difference x minus mu, and that is equal to the variance of x. Then the positive square root of the variance of x is the standard deviation of the random variable x. So let's have an example. Let x have the exponential lambda distribution. It is actually defined in example 2.2.2. And then in that example, we calculated the mean of x to be equal to lambda. Now we're going to compute for the variance of this random variable x. So by definition, it is equal to the expectation of the square, the square of x minus lambda. And then supposedly, if we're going to consider the definition of the expectation, this should be the improper integral of x minus lambda quantity square, and then times the probability density function of our random variable x. And the probability density function, we have 1 over lambda e to the negative x over lambda, and then we have the indicator function on the support of our random variable x. That's actually from 0 to positive infinity. Then we have here dx evaluated from negative infinity to positive infinity. That's the definition of our expectation. Okay, we have this improper integral from negative infinity to positive infinity. And then if we're going to apply now our indicator function, the indicator function is equal to 1 when your x is on the interval 0 to positive infinity, while it is equal to 0 otherwise. Okay, so that is why we have this improper integral now of x minus lambda square 1 minus lambda e to the negative x over lambda dx, and this time it is evaluated from 0 to positive infinity. So wala na dito yung indicator function. And then if we're going to expand the binomial expression x minus lambda square, then we have this. Okay? For us to be able to determine the variance of x here, we can take the property of the integral here, the integral property of the improper integral, which is actually the integral of the sum will be equal to the sum of the integrals. And then you can use your knowledge in calculus for us to be able to compute for this expression, for this improper integral. And you can verify that indeed that the variance of our random variable x will be equal to lambda square. Okay? Uh, say for example, itong term na to. Say example, itong term na to. So we have there 0 to positive infinity, and then lambda will cancel out here. So, or say lambda squared, then we have here 1 minus lambda e to the negative x over lambda, then we have here dx. So we have here, and take now lambda e to the negative x over lambda dx. So we let u here be equal to negative x over lambda. Sabihin natin, no? Kung may u natin is negative x over lambda here. So du will be equal to negative 1 over lambda dx. So so yung du mo, e to the du, dx would be equal to u du. So pwede natin ito, magiging lambda square, negative lambda square, and then we have here, by the way, you're going to transform this first into the limit function, using the limit function before proceeding. We have here, say, lambda. We have the limit of e to the negative x over lambda. We have here dx, then b approaches to, we have here 0 to b, positive infinity. And then dyan mo lang yung substitute yung expression natin kanina. Okay, so that's only for the third term. Mas madali yung sa second term, yung sa first term, yun yung medyo mahirap na part. We have the improper integral of 0, x squared, then 1 over lambda e to the negative x over lambda dx evaluated from 0 to positive infinity. But still, you can apply the techniques of integration, which is integral by parts there, for you to be able to compute for that improper integral. Okay, so let's proceed now to theorem 2.3.4. If x is a random variable with finite variance, then for any constants a and b, then the variance of this linear expression ax plus b will be equal to a squared times the variance of x. So to prove this theorem, we're going to apply the definition. Say the variance of ax plus b by definition, that is equal to the expectation of the square of the random variable or this linear function ax plus b minus the expectation of this linear expression ax plus b. And then since we know that the linearity property holds for the expectation operator here, so the expectation of ax or a times the expectation of x and the expectation of b will just be equal to b. So we have the negative of b for that here, because it's being preceded by a negative sign. So the b on the first term would sum to the negative b on the other term, it will equal to 0. So what remains in our expression inside the expectation, we have a x minus a, the expectation of x, then quantity square. And then if we're going to factor out a there from this, ito a, common, no? Common naman yan. And then the square of that, so we have a square, the expectation of x minus the mean of x, quantity square. And then by definition, this expectation is equal to the variance of x. That's the proof of theorem 2.3.4. We have an alternative formula here in the computation of our variance. So instead of using the definition, let's have this alternative formula in which the variance of x is equal to the expectation of the square of x minus the square of the mean of x. And then we can verify this expanding the binomial expression x minus the mean of x quantity square. So we have this result. And then after that, applying the expectation on each of these terms. Okay, the first term is x squared is random, so we have the expectation of x squared. The only random here in the second term is the random variable x, because e of x is a constant, it's a real number. So we can have 2 times the square of e, the mean of x. And then the last term here, this last term is indeed a constant. The square of a constant is also a constant. So the mean expectation of a constant will just be equal to the constant. So we have this expression. And then simplifying, then we were able to get to the expectation of x squared minus the square of the mean of x. Okay, so we have another example here for the binomial variance. Computing for the binomial variance, let x has a binomial distribution with n number of trials, and the probability of success, we have p, and we have here the point probability on the mass point x. So it is equal to the combination of n taken x at a time times the probability of x times 1 minus p raised to n minus x on the support of the random variable x. So the support here of our distribution from 0, 1, and so on and so forth up to small n. So finite values for x. And then in our previous example, we have already computed that the mean of our random variable is equal to n times p. And if we're going to calculate the variance of x here, we're going to calculate now for the expectation of x squared. Okay, so the expectation of x squared, again, using the definition, we have here the summation of x squared times the probability mass function of x. Okay, ito yung probability mass function ng x natin. And then the summation is over all the mass points of our random variable x. So x here from 0 up to n. And then if we're going to manipulate this series, okay, first we're going to manipulate the binomial coefficient in a manner similar that is being used to the mean of x. So supposing we're going to manipulate this expression, x squared times this combination of n taken x at a time. So if we're going to evaluate that, we were able to get this second equality, because n taken x is n factorial, x factorial times n minus x factorial. Okay, since we know that this x factorial here can be expressed as x times x minus 1 factorial. So ito na yung x minus 1 factorial. Ito yung x niya sa denominator, supposedly that will cancel to the x squared above. So ang may iwan na lang is we have this x value. And then elaborating or simplifying more, this n factorial again, same formula. The n factorial is equal to n times n minus 1 factorial. So we have now the product x times n, and then the remaining expression n minus 1 factorial over x minus 1 factorial times n minus x factorial. That would be the combination of n minus 1 taken x minus 1. And then if we're going to observe that the first term in our summation here, when we take x to be equal to 0, so the first term will be equal to 0. Hence, the expectation of x squared will start, the summation will start when x is equal to 1. And then substituting the expression x squared, no, this product, itong product na to, substitute that. Then we have these results. Okay? And then after that, by changing variables, setting y to be equal to x minus 1, then we have this equality. Okay, equality. So when x is equal to 1, obviously, no, when x is equal to 1, our y here will be equal to 0. So we have here y will be equal to 0. Okay, and then distributing what is inside our summation symbol here. Then we have the summation of the sum will be equal to the sum of the summations. Okay, so we have this expression in the last part. Okay, ang first term, no, the first term would mean that the expression in the summation symbol here will sum up to uh, would sum to equal to 1. Okay, or rather, the first sum is equal to n minus 1 times p. Because for this, we simply have a random variable y having a binomial distribution. Itong y natin dito, having a binomial distribution with n minus 1 uh, number of trials, and the probability of success here is still equal to p. Okay? So itong expression natin dito, yung summation, this is the mean of y. This refers to the mean of y. So yung mean ng y, okay? Uh, yung mean ng y will be equal to n minus 1 times p. That's the mean. Okay? Yung sa first summation natin. So we have np times n minus 1 times p. While the second term, if this is the probability mass function of y, so ito yung yan, no? Yung y natin. So that means the summation over all the support of y based on the property of our probability mass function, this will be equal to 1. So the second term will be just equal to n. So ito yung first term natin, it will be equal to this expression. Okay, so we have already computed for the expectation of the square of x. So the variance of x, using the formula, the expectation of the square of x minus the square of the expectation of x. Okay, so we have this. Ito minus the square. And then simplifying, then we have this. Or this is simply equal to n p q. If we take q to be equal to 1 minus p. Okay, so the variance of our random variable having a binomial distribution with n number of trials and the probability of success is p will be equal to npq. Okay, parang yan yung proof natin. Okay, next we're going to learn another probability function or another function associated with our probability distribution. We call it as the moment generating function, or the MGF. So moment generating function. As the name suggests, the moment generating function can be used to generate moments. But the main use of the MGF here is not to generate moments, but to help in characterizing a distribution. Okay, so let's have here the definition. Let x be a random variable with the CDF big F. The moment generating function, MGF of x, or the moment generating function of the distribution of x, denoted by big M sub big X evaluated at t. Okay, it will be equal to the expectation of e to the tx. tx. Okay. So provided that the expectation exists for t in some neighborhood of 0. Medyo mathematical itong some neighborhood. That means if we have a positive h here, however small, t is between negative h and positive h. So in some neighborhood of 0. And the expectation of e to the tx exists. So if the expectation does not exist in a neighborhood of 0, we say that the moment generating function does not exist. Okay, so we can write the MGF of x depending on the whether our random variable x is continuous or discrete. So the MGF of x, if x is continuous, then we have this improper integral. E to the tx times the probability density function of x dx evaluated from negative infinity to positive infinity. But if x is discrete, then the moment generating function of x will be equal to the summation of e to the tx times the probability mass function of x over, no, the summation is over all the mass points of the random variable x. Okay, so we have here our working formula in computing for the moment generating function of the random variable x. So before illustrating moment generating function to generate the moments, let's consider first this theorem 2.3.7. So if x has an MGF, okay, big M sub big X evaluated at t, then the we know a while ago that this is the nth moment of x. Okay, the nth moment of x, or the expectation of x to the n, will be equal to the itong expression na to. This means that we have the nth derivative of the, or the value of the nth derivative of the moment generating function of x evaluated at t is equal to 0. Okay, ito na ngayon. At t is equal to 0. Okay, so simply it says that the nth moment of a random variable x is equal to the nth derivative of the uh, moment generating function of x evaluated at t is equal to 0. So for the proof of this theorem, we assume, without law, we simply assume here that our x here is continuous. And then after that, we also assume that we can differentiate under the integral sign. So we have this derivative. Say we're going to take the derivative of the moment generating function of x with respect to t. Okay. So first step here is just by substituting what is our moment generating function of x, and then interchanging the functions, the derivative, as well as the integral. So we can differentiate. No, we can differentiate under the integral sign. And then if we're going to take the derivative of e to the tx with respect to t, then we have these results. Okay, so applying the definition, this would be the mean of x and e to the tx. So we have the mean of the product of our random variable x and the exponential function of e to the tx. Taking this as our parang expression and then times the PDF of our x. So that's by definition, we have the expectation of x e to the tx. Then we're going to take the derivative, rather if we're going to evaluate the derivative of the moment generating function with respect to t and then evaluate it at t is equal to 0, then that would be equal to the mean of x. This is simply for the first moment of x. But proceeding in the analogous manner, we can establish that the nth derivative of the mgf of x, the nth derivative with respect to t, and then we're going to evaluate at t is equal to 0, that would be equal to the nth moment of x. Okay, let's have an example to illustrate that the moment generating function really or indeed generate moments. First moment, second moment. So in example 2.1.16, we have encountered a special case of the gamma PDF. This actually refers to the inverted gamma probability density function. Okay, so we have here the PDF 1 over gamma lambda b to the alpha, gamma of alpha b alpha, and then x to the alpha minus 1 times e to the negative x over beta. The support of our distribution here, x greater than 0 but less than infinity, and we take alpha and beta to be positive. By the way, if we're going to use the indicator function here, kasi minsan pag evaluate na kayo, hindi nyo masyadong ginagamit yung indicator function. Sa undergrad, ginagamit yung mga indicator function usually if the reference book is the by MGB, Wood, Graybill, and Boos. So we have here the indicator function, x, and then 0 to positive infinity. And then we have here alpha to be positive as well as beta to be positive. Okay, so this is the gamma function, gamma of alpha. And then if we're going to take now the moment generating function, by the way, our goal here is to determine the moments of our random variable x, some moments of our random variable x. So just to illustrate, let's going to find first the moment generating function of x. Okay, so this is equal to e. So we have here e to the tx, and then you have your probability density function. So we have 1 over gamma of alpha, beta alpha, x of alpha minus 1, e to the negative x over beta. You have your indicator function of x from 0 to positive infinity dx. This is by definition from negative infinity to positive infinity. Yun yung nakita natin kanina, di ba? We have two formula. It depends whether our x is discrete or continuous. So in this case, this is continuous. So on the second equality now, dito na equality, wala na yung indicator function. That is why the integral now is being evaluated from 0 to positive infinity because the indicator function is 0 if x is not an element of the interval 0 to positive infinity. Okay, so we have that. We put the constant before the integral sign. No? Those expressions that does not depend on the random variable or the dx or x, we can put it before the integral sign. By the way, itong part na to, say this part of our probability density function, ito, mas maganda ito na lang yung gagawin natin. Ito, if small f of x is our probability density function, itong naka-blue na expression or product here, we call it as the kernel of our function. So when we say kernel of our function, yan yung maiiwan, no? When we're going to disregard the constant. So, ang constant part dito yung 1 over gamma alpha and then beta to the alpha. So, kernel. No? We call this as the kernel of our function. So, simplifying what is inside our integral sign, then we have this. Okay, so x to the alpha minus 1 and then e to the negative e to the negative of the quantity 1 minus beta minus t of x dx. And then furthermore, we can simplify it in this expression. Okay. This expression now, or the integrand, is actually the kernel. No, it's actually the kernel of our, again, no, of our random variable having a gamma distribution with parameters alpha, and then the other one we have beta 1 minus beta. Now 1 minus beta t. Okay. To see that, say for example, this is our probability density function. We use our alpha here. We take alpha as A and then beta as B. So x here is indeed greater than 0 but less than infinity. And then we have the constants A and B to be positive. So kunwari, ito yung kanyang probability density function. And then we know that if this is a probability density function, using the property of the probability density function, that this will be equal to 1. Okay? Supposedly, we have the integral of your PDF dx evaluated from negative infinity to positive infinity. Ganun man yan. Negative infinity to positive infinity. Your PDF, 1 over gamma a b to the a x to the a minus 1 e to the negative x over b. You have your indicator function x 0 to positive infinity, okay, dx. So equal na yan siya. And this would be equal to 1. Yan yung property ng ating PDF. So this integral of the integral of the kernel of our function is simply equal to gamma of a beta b of a. So ang result nito will be equal to what? 1 over gamma of alpha beta to the alpha. Okay? So yung integral of the kernel will be equal to what? Gamma of, what is your a there? What is the a? This a refers to alpha pa rin. Alpha. And then b. What is your b? It refers to beta 1 minus beta t, and this is being raised to alpha. Okay? Yan yung ating moment rating function of x. Yan, makikita natin yan. Okay, so to simplify further, we have this. And then the gamma of alpha here will cancel out. Beta of alpha also will cancel out. Yan, at saka itong alpha. Then meron pati yung alpha na maiiwan for the denominator. And then this would be 1 over 1 minus beta t raised to alpha. And then if we take here t to be less than 1 over beta. Okay, since we know, itong part na to, ito yung beta natin, ito yung b, it should be greater than 0. So yung yung part na yan would be greater than 0. That is why 1 minus b. Okay. Ito part na to. Pwede naman yan siya ma-express, no? Ito. Pwede naman siya ma-express as 1 over b beta minus t. This should be greater than 0. So we have negative t greater than negative 1 minus beta. So t should be less than 1 over beta. Okay, so that's why we have here. If t should be less than 1 over beta. So if t is greater than or equal to 1 over beta, then the quantity, okay, this quantity in the integrand of 2.3.5 is non-positive, and the integral in 2.3.6 is infinite. So thus, the MGF of the gamma distribution exists only when we consider t to be less than 1 over beta. Okay, so take note that our goal is to be able to determine the moment or the moments of the random variable x. Given in this problem is the probability density function. Say we're going to compute for the moment using the moment generating function. Though we can compute for the moment using the definition, no? Mas madali naman ang pag-compute ng moment using the definition. But if we're going to use the moment generating function, kung meron itong moment generating function, say we're going to take the first moment, we're going to find the first moment, so we're going to find the first derivative. We're going to take the derivative of the MGF, moment generating function, with respect to t, and then after that, we're going to evaluate at t equal to 0. Okay, so ito yung gagawin natin. So the mean of x, we take the derivative of our moment generating function with respect to t, and after that, we're going to evaluate it at t is equal to 0. Ito lang naman yung ating moment. No? So this is the same as, ito siya. This would be the same as 1 over alpha. Actually, for any alpha to be positive there, we have there. And then we have 1 minus beta t to the negative alpha. So we're going to take the derivative of that with respect to t. So we have there negative alpha, 1 minus beta t, negative alpha minus 1, and then times negative beta. So negative alpha times negative beta. So we have here positive alpha beta. Okay, alpha beta. And then yung exponent natin na negative alpha minus 1, that would be equal to negative alpha plus 1, quantity, no? Alpha plus 1. Then you're going to put that in the denominator. We have here alpha plus 1. Then we're going to evaluate that at t is equal to 0. Therefore, we have our mean to be equal to alpha beta. So this is just an illustration of generating our moments if we have our moment generating function. Though in this problem, hindi naman given yung moment generating function, we solve first for the moment generating function, then after that, we evaluate the first moment. Second moment, in the same manner, no? Pareho pa rin yung take the derivative, the second derivative of our moment generating function, and after that, with respect to t, then we're going to evaluate that at t is equal to 0. Then after computing for the second moment, you can now compute for the variance of our random variable x. Using the formula, it is equal to the expectation of the second moment, expectation of x squared. So the second moment minus the square of the first moment. So I've been saying this in terms of moments. Another example. Before we go to the next example, any questions or clarifications? Is it clear?
Yes, sir.
Okay, thank you, LJ. How about the others? Mary Jane, any clarification?
Okay na, sir.
Okay, Len. Okay, let me proceed now. Okay, Second illustration of calculating a moment. Calculating the moment rating function. Say we have a binomial distribution with n number of trials, and the probability of success is p. Okay, so using our formula for the moment rating function, having a discrete random variable, so we have here the summation of e to the tx times the probability mass function of our random variable x. Ito. Okay, x from 0 to n on the support of our random variable x. Then simplifying, we have here the product p e to the t raised to x, and then 1 minus p raised to n minus x. We're going to use the binomial formula here to compute for the moment rating function of x. So consider first this expression in terms of u and v. So the finite summation of n choose r, u to the x, v to the n minus x, as x summation ranges from x equals 0 to n. This is equal to the nth power of u plus v. Okay, that's our binomial formula. Okay, so if we're going to look at our expression here, we can take u here to be equal to p e to the t, and then v to be equal to 1 minus p. And then using this binomial formula, then we have our moment rating function of x. Madali lang masyado, no? Okay, so if the moment generating function can be used to compute for the moment, the moments, but primarily the moment generating function is being used to characterize our the distribution of our random variable. And it says here, we have here a remark. There are, however, some technical difficulties associated with using moments to characterize a distribution. So if the moment generating function exists, it characterizes an infinite set of moments. Take note of that. Now, kung meron tayong moment generating function, it characterizes an infinite set of moments. However, if we characterize it by the infinite set of moments, does it uniquely determines a distribution function? Pabaliktad naman tayo. Okay, so to answer that question, unfortunately, the answer for that will be no. There are random or distinct random variable having the same moments. So it does not mean na pag characterize natin yung moments, then we can uniquely determine the distribution or the random variable or the distribution of our random variable. So let's have this theorem, theorem 2.3.11. Okay, so this theorem actually shows how a distribution can be characterized. So let big F of x and big F of y to be two CDFs, all of whose moments exist. Then letter A, if x and y have bounded support, medyo mathematical masyado ito, no? Have bounded support, then the CDF of x evaluated at u is equal to the CDF of y evaluated at u for all u, if and only if the rth moment of x is equal to the rth moment of y for all integers r, 0, 1, 2, and so on and so forth. So we have a biconditional statement here. We have the assumption that x and y have bounded support. It says here that the CDF of x evaluated at u equal to the CDF of y evaluated at u for all u, if and only if. Equal yan if and only if the rth moment of x is equal to the rth moment of y for all integers. I'll say for all positive integers and for all non-negative integers are kasi kasali na itong 0. And then another, if the moment generating functions exist, okay, both the uh, big M sub x and then big M sub y evaluated at t, and if we no, they both exist, and if they are equal yung kanilang moment generating function evaluated at t for all t in some neighborhood of 0, then equal yung kanilang moment generating function, then the CDF, big F of x evaluated at u should be equal to big F sub y evaluated at u for all. Okay, sa letter B, hindi siya by conditional statement. We have only a conditional statement. If moment generating function exists and then they are equal, okay, and then they're equal for all t in some neighborhood of 0, then the implication with it, then the CDF of x evaluated at u should be equal to the CDF of y evaluated at u. Okay, so if you want to know the proof of that, you can refer to the book of Casella and Berger. Let's proceed now to theorem 2.3.12. We have convergence of the moment generating functions. Suppose we have this sequence of x sub I, 1, 2, and so on and so forth. That means we have an infinite sequence here of random variables, x sub I. The other term for this sequence, we can say we have a stochastic process. Okay. Malalaman nyo na yan, no? Kung kukuha kayo ng stochastic process na subject. So we have a sequence of infinite random variables, x sub I. And then each with moment generating function, big M sub x sub I evaluated at t. And furthermore, suppose that the limit of the moment generating function, big M of x sub I evaluated at t approaches to infinity, rather at I approaches to infinity, will be equal to this moment generating function of x evaluated at t. That is an MGF for all t in the neighborhood of 0. So that means na yung sequence natin, no, meron tayong sequence of random variables x sub I, yung limiting moment generating function of this sequence of random variables x sub I equal siya sa moment generating function of x. Okay, that's the assumption. Suppose, no, that's the assumption. Then there exists a CDF big F of x whose moments are determined by this moment generating function of x. So there exists a unique, no, CDF big F. That is for all x where the CDF is continuous. So we have, that would also imply that we have that the limiting cumulative distribution ng ating sequence of random variables x sub I as I approaches to infinity will be equal to big F sub x evaluated at x. So that is convergence for all absolute value of t less than h. This is because of some neighborhood of 0. H having h to be positive, however small, your t should be greater than or between the negative h to positive h. So the convergence of MGFs to an MGF, the implication niya, convergence of the MGFs, that is our assumption, it would imply convergence of CDFs. Ito yung una, convergence of MGFs implies convergence of CDFs. So the proofs of theorem 2.3.11 and then 2.3.12 rely on the theory of Laplace transforms. Okay, that's why hindi ko na lang in-explain yung proof nito. You can review if you want regarding Laplace transforms. But let's going to have an illustration to this theorem, or these two theorems. Let's have this Poisson approximation. One approximation that is usually taught in elementary statistics courses is that binomial probabilities can be approximated by Poisson probabilities. Say the binomial distribution, we know that it is characterized by two parameters, the number of trials, n, and then the probability of success, we have p, while the Poisson distribution is being characterized by only one parameter, we have lambda. So the Poisson approximation is valid when the number of trials is large, it approaches to infinity, and then the product NP, or that means the mean. If the mean of the random variable having a binomial distribution is small, then we can use this approximation. So the Poisson lambda probability mass function is given by this. Okay, so we have e to the negative lambda to the x over x factorial. So that means itong x na to, for this particular definition, this x has a Poisson. Okay, it's a Poisson distribution with parameter lambda. So the approximation states that if x, ito ngayon yung gagamitin natin, no? Itong x na to. Hindi itong nagre-refer, just an illustration of the probability mass function of the Poisson distribution. So if x has a binomial distribution with parameters np, and then y has a Poisson distribution with parameter lambda, then if we let lambda here to be equal to np, lambda to be equal to np, then the point probability that x is equal to x is approximately equal to the point probability of y to be equal to x, evaluated at x, will be equal to this real number, or the real value x, for large n and then for small n minus b. Okay, so we shall now show that the MGF converge. If the MGF converge, then after that, we can invoke our theorem that the CDF also converge. Okay, so this is the, we have computed this a while ago. This is the moment generating function of our random variable x having a binomial distribution. And then you can verify. This is in exercise 2.33. I think you have solved this in your undergrad. Compute for the moment generating function of your random variable x having, or y having a Poisson distribution. Madali lang naman ito. So you can please verify. Please verify this. We have that. So meron tayong dalawang moment generating function. Okay, let us try to check now that we have convergence in MGF would imply convergence in CDFs. Okay, so if we define P here to be equal to lambda over n, okay, since we know that lambda here is equal to NP. Okay, we have that. We take our parameter lambda to be equal to the mean of our random variable x. So P is equal to lambda over n, then the moment generating function, ito yun, verify natin. The moment generating function of the random variable x evaluated at t will approach to the moment generating function of y evaluated at t as n approaches to positive infinity. So to show this, we're going to use this lemma 2.3.14. So let me read first lemma 2.3.14. Let a sub 1, a sub 2, and so on and so forth be a sequence of numbers converging to a. So that is the limit of a sub n as n approaches to infinity will be equal to a. So by definition, sequence of numbers converging to a, pointwise convergence. Okay, then it says here that the limit, if we have this expression of the nth power of 1 plus a sub n over n as n approaches to infinity will be equal to e to the we're gonna need to verify, no? This is a lemma, and then we're going to use this in say in showing that the moment rating function converge. Okay, so this is the moment rating function of x. Itong part na to. Okay, so we can write this as 1, 1 plus, we can factor out p here, then the remaining expression now, e to the t minus minus 1, then quantity raised to n. So yung p natin is lambda over n. Kaya ito yung diretso na. Diretso na yan. Lambda over n. Kasi so lambda over n, yan yung p. Lambda over n. So, yung expression natin yan dito is almost similar to this. Okay? 1 plus yung denominator yung n. So, ano yung a sub n dyan? So, we can let the a sub n here to be equal to a there, no? Equal to a, and that is e to the t minus 1 times lambda. And then applying now lemma 2.3.14, here, the lemma of the moment rating function of x, we're going to evaluate that. We have this result, and this expression is actually the moment rating function of the random variable y having a Poisson distribution. So the moment rating function of the Poisson. Okay. So we close this section with a useful result concerning the moment generating functions. So for any constants a and b by the MGF of a random variable ax plus b is given by this. So this is our function of our random variable is also a random variable. Diba? Nakuha natin yan. Say y is equal to g of x. A transformation of our random variable x is a random variable. So the moment generating function of ax plus b evaluated at t will be equal to e to the vt times the moment generating function of x. This time evaluated at the product at. So this is easy to prove. We just apply the definition. So from here, we apply the definition. So the expectation of e to the random variable, which is a function of x. So e to ax plus b times t. And then the properties of exponential. And then we can take the constant before the expectation operator. And then applying again the definition of MGF. This time we have the moment rating function of x, but evaluated at the product at. And so we have proved the theorem. Okay, so later this theorem will be useful when we go to chapter 4. Okay, so the time is already 4:31, and this is the last part of chapter 2. Any questions before we go? By the way, tomorrow we will start at chapter 2, but first I'm going to give the yung first part dyan as a reading assignment. Any questions or clarifications before we go? Guys?
None, sir.
And so first, sir.
Okay, so that's all for this afternoon. And class dismiss. Bye for now.
Then,
Going to-
please.
Thank you, sir.
going to
Thank you,
start
sir.
Okay, bye.
Dede,
Bye, sir.
Oh, bye.
Dede, you know,